Hello guys, welcome back to Plaxis tutorials. In this lesson I'm going to explain how to simulate plate load test using Plaxis 3D. As we know, the plate load test is one of the important geotechnical field tests, and it's used to estimate the ultimate bearing capacity of the foundation. Before I go to Plaxis, I will briefly talk about plate load test procedures according to ASTM designation 1194-94. First, the thickness of the plate should not be less than 25 millimeters, and circular plates with diameter 305 millimeter to 762 millimeter are used. For conducting a plate load test, we should excavate a pit of size not less than 4 to 5 times the size of the plate, and the bottom of the pit should be at the same level of the proposed foundation. After the plate load test is installed, after installing the plate load test, then the load is applied to the plate by using a hydraulic jack in increments. The load is increased until there is a definite failure of the soil, or until the settlement of the plate reaches about 10% of the plate width or the diameter. After that, the load is then removed incrementally. After finishing the test, pressure versus settlement curve is plotted from the data obtained from this test, and ultimate bearing capacity of the plate is determined from the pressure settlement curve. In our example, we are going to use this data, loading and unloading. For loading, we increase the load from 0 to 35. In each phase, we increase the load by 5 kilonewton. After that, we unload the plate until 0. The advantage of plate load test, we can estimate the ultimate bearing capacity of the shallow foundation. For example, for clay soil, the ultimate bearing capacity of the foundation equal the ultimate bearing capacity of the plate. Also, for sandy soil, the ultimate bearing capacity of foundation equal ultimate bearing capacity of plate multiplied by width or diameter of the foundation divided by width or diameter of the plate. We are going to simulate a plate load test using Plaxis 3D by using this data. Okay, now we open a Plaxis and make a new project. I type plate load test. To reduce the effect of boundary condition, I'm going to make a soil geometry 10 meter by 10 meter, which is minus 5, 5, minus 5, 5. First we define a borehole, and depth of borehole we assume 5 meter. In our example, we assume that we don't have a water table, so I put the head minus 5, and I define a material for our soil, which is a clay soil. We're going to use more column and drain criteria to model our soil. The unit weight of the soil is 17 kilonewton per cubic meter, and the elasticity of the soil is 18 megapascal, which is 18,000 kilonewton per square meter, and Poisson ratio is 0.3. The cohesion is 20 kilonewton per square meter, and internal friction angle is 20. Okay, we assign the soil to our borehole. Okay, now we finish defining the soil geometry and properties of the borehole. After that we go to structure stage. In structure state, I have to excavate a pit with dimension 1.5 by 1.5 meter and to a depth 0.5 meter. By using create a surface, and I go to option visualization setting. I type 0.25 to make it easy for drawing. So like that. Now I have 1.5 meter by 1.5 meter. We extrude this surface to minus 0.5 and I delete this. So now I'm going to create a plate so I can hide this volume. To create a circular plate we use this option in Plaxis, which is called designer. I click here and go to segment, add section, arc. The plate we are going to use in our example has a diameter 305 millimeter. So the radius will become 0.1525 meters and 300 degrees. We have to move it to a center, minus 0.725. Also I have to move it to the bottom of the pit, which is minus 0.5. I have to make it to a surface and create a plate. To create and to model an interface between plate and soil, we also can add a negative interface. Now I can define a new material for steel plate. We choose plate, new, steel plate. Thickness is 0.025 meters and unit weight 78.5. Elasticity is 200 million kilonewton per square meter, and the Poisson ratio is 0.3 we are going to use. Okay, and we assign steel material to steel plate. Okay. Also we are going to create a point load at the center of the plate, like that. Okay, now we finished our modeling and materials. We go to mesh stage, create mesh, define mesh. Okay. After that we go to staged construction. So in the staged construction we are going to define the stage for excavation, for installing a plate, and for loading and unloading. We go to edit phase. We add a phase for excavation and next phase for installing the plate. After that we start loading with 500 kilonewton. And another phase we increase to 10 kilonewton. And next increase to 15 kilonewton, 20 kilonewton, 25 kilonewton, 30 kilonewton, 35 kilonewton. After that we start to unloading the plate, and we type unloading and we start from 30. Next unloading 25 kilonewton. Next 20. Next 50, and the last unloading is 0 kilonewton. So in the first loading we reset displacement to 0 from previous phases. Okay. So in the excavation phase we deactivate the excavation volume, and in the installing plate we activate plate and interface. In the stage of loading we keep the amount of load minus 5 kilonewton. For loading 10 type minus 10, and so on. So now everything is finished and our model is ready to calculate. Okay, I click calculate, ignore feedback and calculate. Okay, the analysis is finished and we don't have any problem. So we save our model and we go to result. So in result we go to total displacement and use it, displacement in z direction. For 500 kilonewton we have minus 0.6346 times 10 to the power minus 3 meter, and for 10 kilonewton, as we see, the settlement is increased, and 25 settlement is increased, 35 kilonewton settlement is increased, and for unloading settlement is decreased. I have already prepared in this Excel sheet the amount of loading and unloading and corresponding settlement. Also in here, the load per unit area, I divide the amount of load to area of the plate. Also I multiply the settlement by 1000 to convert from meter to millimeters, and here I plot the relationship between the pressure, which is kilonewton per meter square, with settlement in millimeter. As we see, by increasing the load, also the settlement is increased. Also when we start unloading, some of the settlement is reversed, and this is called elastic settlement. By tangent method, we make a tangent line from the early curve of the load settlement curve and another tangent line from the last portion of the curves. The intersection of these two tangent line is the ultimate bearing capacity of the soil, and in here I calculated approximately, which is equal 390 kilonewton per square meter. If we assume that the factor of safety is 2, the allowable bearing capacity will be 192. Okay, thank you for watching, and please do not forget to subscribe my channel. Thank you.